the idea was try to see how quantum computing could be useful for numerical general relativity. So when I was looking for the connections, I really didn't find much, didn't find at all yet how quantum computing was applied to this area. But my ambitions for this year and the next one is to bring quantum computing for industrial problems and fundamental problems of physics. So here in this presentation, what we're going to do today, the presentation, my talk will be divided into 3 parts. The first part will be about basics elements of quantum computing. The second part would be about playground with Jupyter Notebook. Also, in a way, simple stuff, especially for all of you who are solving Einstein's equations and so on. And the third part of my talk is going to be about possible insights, how we could connect general relativity for solving nonlinear differential equations with quantum computing algorithms. More precisely, I'll show you some results from a group, how quantum neural networks were applied for some nonlinear differential equations. And yeah, so that's our outline for today. So first, we will start with the history of quantum computing. Now, everybody knows about how Richard Feynman in the 80s offered this proposal about that nature isn't classical. And if you want to simulate nature on a quantum level, the best system to simulate is quantum system, so quantum computer. But not many know that independently also Russian mathematician Yuri Manin, in his book Computable and Uncomputable, made some notes about limitations of classical algorithms. And he also offered this idea that simulating physical processes as quantum systems, that would be a good idea to use quantum computers for this purpose. And so basically, quantum computing is the intersection between quantum mechanics and computer science and information theory and so on. So quantum mechanics, computer science, they were developing independently. And so until Randall from IBM pointed out that if the computer was made reversible, the heat consumption would be greatly reduced. Well, I didn't go deeply in this topic, but I guess the idea here is about some unitary operations because they're reversible. Then, as we just discussed with Feynman and Manin, first quantum algorithm, Shor, and so on. And where are we now? Right now, we are in the era of so-called noisy quantum computers. We already have quantum computers from IBM. I don't know, I guess the maximum amount of qubits by IBM, like 400 something. On single atoms, also we use single cold atoms, it's like 1000 something. And D-Wave, they use analog quantum computing, and they actually offered more than 5000 and so on. So for some optimization problems. So basically, by this moment, we already have quantum computers to work with. But they are not perfect. So that's the thing. So some of your quantum algorithms you can run on real quantum computers or on GPUs. So now classical computing. So in classical computing, we have bit, and the system would be in defined state, either 0 or 1. And bit will be completely independent one of another. And we have some classical operations, like those are truth tables. You're probably familiar with them because you're computational scientists, researchers. So like I'm a theoretical physicist, I'm not from computer science, so it's not like, you know more about this stuff probably. And those are representation of logical gates in classical computing, where they will perform, the combination of them will perform some arithmetic operations such as addition, subtraction, multiplication, and division. All right, now let's quickly move to quantum computing. So I was told that the audience knows about quantum mechanics. That's why I didn't discuss quantum mechanics at all here. But when I teach quantum computing, I always start from quantum mechanics because it's just a really logical transition. For instance, here, now we don't work with a bit which will be either in state 1 or 0. We will work with so-called quantum bit, which is called qubit. But qubit is actually nothing more than wave function written in a two-dimensional basis. Because for wave function, you can write this linear combination, because wave function, as you know from quantum mechanics, are based Schrödinger equation, which is linear differential equation, and the solutions of Schrödinger equations, they linear combination of solutions also will be solutions. So this is just the property of differential equation. And from this property, we get the superposition for wave function. And here wave function is written with Dirac notations. And the coefficients before 0 and 1, which we're gonna also define those notations, it's get notations in the next slide. The coefficients are complex functions. The square modulus of them represents the probability of the qubit to be measured in a particular state, either 0 or 1. So basically, in quantum case, you do not know in what state your system is, can be prepared in a superposition with the probability distribution. But after the measurement, which you will have to do, you will know the probability of being in one or the other state. So those are just the definitions of, okay, I have a little bit of this. I was checking before. Okay, some spontaneous error occurred. So V represents the states 0 and 1, which actually form bases like this. So this is called ket vector, and it's just a column. And this is also ket vector. If you do complex conjugation and transposition, you will get bra vector. In our Jupyter notebook, we will see both vectors, bra and ket. So this approach, it's from linear algebra. It was brought by Dirac, and he just invented it. Basically, he brought it to quantum mechanics to simplify some calculations. So in this linear algebraic approach, basically, you just work with matrices. You can represent your wave function or vector state or qubit. As you want to see, you already have synonymous names here in this as this vector. Here you can see the geometric representation of qubit, which I probably don't have time today to discuss, but it's a block sphere. It's an analogy how we represent a complex number on a plane with like the exponential form. So something similar works for a qubit, and so then you can represent it on this block sphere. Most popular libraries for quantum computing are Qiskit and PennyLane. There are other, of course, but these are just the most famous ones. PennyLane, in fact, connected to our group and offered to work together on the course, because we're also developing, and I'm one of co-authors, quantum computing course. It will be called Classical Information and Quantum Information. And we will use PennyLane in this course. So when it will be ready, you can contact to me or give me your contacts. I will contact you back. But for now, for today, we're gonna study with Qiskit. So first, before we start, let's define now the operations which will transform a qubit. So in quantum mechanics, we say we have operators, which are also matrices. Here we use this slang, so-called gates, because before we discussed gates in classical computing. So now we say quantum logical gate. And those matrices are nothing more as Pauli matrices from Dirac equation. So X, Y, Z. I didn't present here Y, but yeah, it's just similar to this. It's just here I, imaginary unit, minus Y. Yeah, and also we have, so those gates, quantum logical gates, are working on single qubit. You can see it by the dimension of this matrix, right? Because if the dimension was 4 times 4, it would work on 2 qubits. Okay, so how Pauli X works? Pauli X acts upon your vector 0, and it flips it. So you just do this multiplication. And the same it does to vector 1. So that's why we call this Pauli X bit flip gate. Also, we can, also this X gate creates rotation of your qubit, like by pi around x-axis, and other Pauli gates do the same, but around other x-axis. And also we can define, I didn't present here the formula, but you can easily find it. It's a Ry, it's also rotational gate. And here you can see on this block sphere, what happens with the qubit. So the qubit just goes from one state to another. Pauli Z. So Pauli Z, you can also multiply, act upon your basis, and you will see that it does nothing to your zero state, and it gives you a phase, right? Because -1 is the exponential, is the phase. So it will also rotate your qubit if it's qubit in the state 1. So if you apply this to the state psi, then you will, this term will not change, and this term will gain the minus in front of it. Also, by the way, we call 0 and 1 Z bases, because those 0 and 1, by the rules of linear algebra, because their eigenvalues after acting with this operator will be +1, -1. And so 0 and 1, they are eigenstates for this operator. So that's why when we work in quantum computing, we say we prepare a quantum circuit in a Z basis or something like that. This Adamar gate. Remember, we discussed superposition. Okay, so if I start, for instance, from 0 state, how can I create superposition? How I can come to 0 + 1? So it turns out you can do it with this Adamar gate. So this is just simple multiplication. I can share the slides after if you want, and you can just repeat all the calculations. Or in fact, all the popular libraries, they also have this part. So right now, we would just do it by hand, but we don't have time. So I'm just presenting it, just walking with you through it. So as you can see, Adamar gate, when it acts upon 0 or 1, it creates this superposition. We call the state plus and minus state. So it's like going to other bases, like the switching bases here. Okay. Also, we have other important property. It's called entanglement. Entanglement is this property when basically the properties of one qubit are not statistically independent on the properties of other. They are statistically kind of connected. And mathematically, we would say that if the system cannot be separable, presented in a separable way, I mean, the wave function, then you will say that the subsystems are entangled inside. And so here you can see the example of entanglement state. It's a Bell state, it's maximal entanglement state. And also, let's consider the operator which will create this entanglement. So it's called C0. And for this operator, the first qubit here is 0. It's called control qubit. The second one is called target. So basically, one qubit is control, one is target, which means what? Depending on the state of your control qubit, the target state will change or will not change. If control qubit in the state 0, then the target one will not change. If it's in the state 1, then it will change. So that's how it acts. Here you see a simple, it's like one of the original algorithms, like Grover algorithms, and how quantum circuit would look like. This is what we will try to do today, but probably not like completely like this circuit. Unfortunately, we don't have time to consider the algorithm, but my idea was to make you interested and to lower the potential threshold for you to start with quantum computing. So today we will start just a little bit of coding, and then you will feel comfortable to proceed on your own. That's the idea. All right. And so, okay, now it's the second part, but I will try to share I will stop sharing because I would need to share Jupyter Notebook. Just a second.
And this notebook should be similar to the quantum.ipynb notebook available on the tutorial server.
Okay. Okay, my Jupyter notebook is in a different place, but you already have it, right? Let me. Okay, I'm opening. Yeah, Google. Okay, so my Jupyter notebook is being open in the other browser, and I'm trying to see how I can share it. Maybe Steven, for now, not to spend time, can share his screen with Jupyter while I'm trying to put my screen on Jupyter. Because I can share Google Chrome, but I cannot share Bing somehow, and my Jupyter is open in another browser. Like, yes.
I'm sharing it, Victoria.
Okay, thank you so much.
You can just talk about it.
So, yes, the idea for me was actually to to run in front of you, but okay. I mean, I still have my the idea was to run in front of you and to code it. Maybe still will help me because we actually we prepared, guys. Okay, so we ran all the, and I can just say what we're gonna run, and so Steven is gonna be my hands. So yeah, I don't know why, like I had some problems with Ubuntu and Zoom, so otherwise I would just share from my laptop. Okay, so what we're doing here. So when you have your clean system, right? So first what you do, you install Python, but of course you have Python, and then you install Jupyter, you have installing Qiskit. Then after you installing Qiskit, yeah, with Qiskit, right? So now we're going to import all the libraries, what we will need. So from Qiskit visualization, we import those libraries, array to LaTeX. We'll need it to represent ket and bra vectors, then state vector, and so on. So just this one, we just copy. Now, we just studied today vectors and direct notations. So guys, check this out. So this is how you will write the ket vector, ket0. So by using like the set of two square brackets. Okay, so if we run, I think we should run, right? We should run the ket one. Okay, so Steven, can you scroll a little bit? Okay, so as you can see, after you apply array to LaTeX, you see your column 1, 0. Just I didn't lie, just exactly how we studied before. Now let's do the same with the Hermitian conjugated, how we say, right? It's like transposed and complex conjugated. Okay, so okay. Here, okay, next time. So the idea is that we have to give a student a little bit of like time, but it will be okay. So example 1, create 1 and 1 with Python list. So okay, I think that here we're already demonstrating the with sort of Okay, so let's build the
Yeah,
same for
sorry,
bra,
sorry, I had my
one
answer
and
here.
bra and cat one. So let's run it. But it's kind of exercise. But so I want the students to try a little bit here at some point, like maybe not with everything, but because otherwise they will just feel like just a lecture, not a.
Yeah, I'm sorry, I didn't mean to
Okay,
fill
so what
that
are we
in.
doing here? So let's run this. Let's run bra one and cat one. We should, because we should now to represent guys, right? We should write array to later, bra one and cat one to represent. So we can add one line after bra one and cat one, or here, just because it escape B, right? Like a Jupyter notebook. Oh yeah, here array to later, array underline to later, yeah, and bra zero, bra one. Yeah, I'm sorry, bra one and then after that cat one. Exactly. Okay, so I think it shows us kind of the first one. Yeah. Uh-huh. Okay, perfect. So now we can see that the bra vector, it should be a row because we did transposition, right? All right, next move to the next one. So how are we going to act with the zero, guys? So what I have 33 minutes. The 33 minutes is, I was told 45 for the talk, 15 for the questions. So I have like 15 something minutes. All right, so how are we gonna write? Write zero. But okay, bra zero, we actually kind of okay, bra zero, it's gonna be 1 and 0, true. Okay, and then we immediately do array to later, bra zero, just to display. Nice. Now it should repeat the same for cat, right? So here we did this one, the left one. Together they form bracket. So yeah, now we can copy just bra zero, we can copy the line and just to put, yeah, I'll just write 0 and 1. All right, and array to later. Nice. Okay, so yeah, this is okay. So let's go further to Qiskit state vector class. I guess the idea of this module will be about normalization. So what was some kind of mistake? No, I mean, look nice. Yeah, so Qiskit vector class. So before, when we discussed the vector, the wave function of qubit, we saw, no, we actually didn't see alpha and beta, right? They are complex amplitudes in general, but they also can be sometimes real ones, right? So the idea is that you can use this library, like state vector, for instance, this line, the first line, when you apply state vector to your bra, you'll get this matrix form, right? So it's already different format. And then you can apply draw. Yeah, you can run this line. Yeah, so it actually gives you this beautiful representation as we just saw before. So now let's do the furthest step. Yeah, so what we can do by using state vector, we can create some, this actually, I didn't teach you, but it's a tensor product. When you have 0, 0, it means that you multiply by like a tensor operation to vectors. So you actually expanded your, now you work not in 2-dimensional space, now you work in 4-dimensional space. Like I didn't put the slides about teaching tensor product, but maybe you know. So the idea is that when you have now this already 2-qubit system, right? It's a 2-qubit system, and then we draw by using this draw operation. So now we want to do what? The idea is here to Yeah, so let's run this line. It will basically give you this exactly. So now there is an operation if we can check, when we can check that the vector is normalized. So if we apply, now let's try to apply to u, right? Because u is actually normalized. Like we can even do it in the same line if you want, Steve. Just or the next one, yeah. So instead of applying is valid to SV EQ, we can apply to U. Yes, just U and is valid because U. Oh yeah. So guys, the idea is here is that because the coefficients are complex functions and there are probability amplitudes. This okay. So here, no, U is defined. U is defined above, so we can just write U underline. No, U dot. After U, we put dot. Yeah, and then we put is underline valid and brackets. Because we already defined it. Okay, now we can run. All right. So okay, no, I'm sorry. It's not you. It's not you because you is a draw one. It's SV underline EQ test, the test one. Okay. When we were doing, yes, test one. This one, yeah, as you can see. So I'll explain what it means from physics perspective. So the physical meaning in quantum mechanics only has the probability, and because of that, when you're gonna do integration or summation over the whole space of the whole universe, the probability cannot be more than one. It's normalization. So that's why when you sum the squares modulus of those probability amplitudes, you have to get one. And this is inside of this library, like it's valid, it's inside of Qiskit. So I think your homework here can be like, we don't need to do it now. It's going to be interesting homework. Create your own valid state vector. So this is, I think Stephen was playing here. Let's check it, by the way. Let's check if it's valid. I feel like, well, yeah, okay, it's gonna be right because it's 9 plus 16, so it's gonna be valid. But what if we put different? Like we can put different and you will see that it will not work, right? It's gonna be false. So your homework, and by the way, Stephen used two-dimensional basis, but you can play even kind of stronger and also use your computational skills. Because once I was teaching a class and one student called it normalization procedure, right? So you can use some like normalize my state, like you can play with this part. Okay, let's go for the next part, Qiskit operator class. So Qiskit operator class is also can be used to represent, yeah, we can just, yeah, here we can just run the lines, I believe. Okay, let's scroll a bit. Yeah. So we should apply different operator class here. I guess it's convenient further on to define gates. Okay, also this part, inner and outer product. I also didn't present on the slide, so I'm sorry, but you know what is inner product from calculus, right? So when you multiply row by column, it's going to be your, yeah. So for instance, if you do, wait a second, okay, okay, go a little bit up. So inner product here in Qiskit is denoted by dot. And so it's dot product. So the output is a scalar. So that's why we get one. But outer product, in fact, it's a projector operator, right? Because we are multiplying what? Column by row. So it will create your matrix. You also can check it by hand. And this is your result. Okay. I believe the next exercise can be homework. Just play with it because you have your notebook saved. So just play and try to display all of this. Let's try to see the next module, simulating measurements using state vector. So we can write state vector, several ones, and then we can display. So we can run this one. All right. Okay. And so, yeah, state vector has this valid class, and also we can display. Now we can play with I think we need to do this. It only displayed one, right? It displayed because in Python, I don't know. Ah, no, it displayed because it's text. I see. Yeah, of course. No, no problem. Yeah. Okay. So yeah, you can see that one vector is normalized. It's true, and the other vector is not normalized. Yeah. Okay. Simulating measurements is using state vector. Again, let's define V state vector as such, and let's draw it. Okay. So now you can see that amplitude, probability amplitudes can be complex. All right. And what's next? So the important idea here that complex numbers, complex functions, okay, wait. So complex numbers, complex functions cannot be measured by detectors. Like yesterday we talked with the group and like what is photon? It's a click on detector. So photon is more complicated than just click on detector in theory. But the idea is that it's like some say it's a collapse of wave function, but mathematically it's an inner product, right? So you do this dot product. Let's say, okay, I will show you later on, but this measure procedure will basically turn your complex amplitudes into real ones. You can see it, right? Okay, so for now we can just see that after measurements, we got the probability of observing a specific state. For instance, here you can see that your state is 0 because in quotes, right? And the probability, can we see it? It's below a little bit. Yeah. Yeah, well, you would have to do square modulus of this, yeah, 1/2. Particular example vector defined above, the measure method defines the quantum state vector after the measurement. So in order to calculate the probability of your qubits being measured in the state 0, right, you will have to do the square modulus. Okay, let's go below. Let's see some operators. Oh yeah, that's exactly. By the way, try to run it again and you will see that the number on the column will be different. Now it's 5438. So quantum mechanics is probabilistic science, right? And so you will see, yeah, it changed, right? Because it was different, you can see. So it's almost 50-50, then you can observe. When it's 50-50, it means the state is random. When it's in superposition, then it's a random state. You cannot, like, it's not bringing any information. But here, more probability that you will observe your state, your qubit in the state is 0. When you're going to build your own quantum circuits to solve your own problems, be it optimization or solving differential equations, you will get like distribution like this. It's not going to be just 2 columns. It's probably going to be several. And you will measure your state. Oh, yeah. Okay, so I see Steven is playing with the count. Yeah, if you, but you can also increase. You can to 10,000. But for 10,000, I think it's also, yeah, I mean, it's kind of almost equal. But the idea is that when you create a specific algorithm for the solution, right? You will get the higher column for some specific state which you want to find. For instance, it works for time optimization problems like in finance or yeah. But okay, let's go further. Let's go to operator. Scroll a little bit. So by using this class operator, you can act and transform your qubit. For instance, yeah, okay, so we draw and let's try now. So this is, I'm just showing how you can encode the operator, but let's write some kind of simple quantum circuit. Yeah, and okay, let's try to run this one because we can, yeah, we're talking about how sometimes you can visualize, but I think it's already installed. You can visualize. This doesn't work in Python 3.8. Okay, guys, so this is the idea that if you just apply circuit, okay, let me first describe the code, what you see here. From Qiskit, import quantum circuit. After that, you see circuit equals to quantum circuit 1. 1 means you have 1 qubit. That's why it's a 42, right? eternal answer. So you see that it's 1-qubit system, and then you just created it. By default, we always create in a state 0, by the way, in this Z basis. Then you apply Adamar gate, which we studied before. Here, they use little h, not capital. And you say, I'm applying to my first qubit. We start counting from 0. So Adamar h, and if it was 2-qubit system, I would put, for instance, 1, it would be second qubit. Then you apply some other gate, like a T gate, Toffoli gate here, like then Adamar, and so on and so on. So here I'm just showing how it would, the line from some quantum circuit would look like. Also, let's go down quantum. Yeah, and also for beautiful visualization, you can use this line, but you will have to install or update your Python. Yeah, Qiskit doesn't provide this visualization line, but I found it. Okay, so let's try to do block sphere. Let's see if it works. Okay, so here's what we're doing. I like how fast Steven is. I like how she's helping today. So what we did, so we again applied all the gates, all the Pauli gates, and we printed. We say quantum circuit dot apply the gate, print the result. Okay, let's try. Okay, Adamar. Okay. And the ending of our Jupyter is let's define block sphere. Okay. Return class. Okay. And now you use it. Okay, this is beautiful. So now you use this state vector. Do you see what happened? You started from the state 0. You applied. Can you go a little bit up when we are defining the block sphere? So you can see that in the definition of this function, you in the definition, the only one operation is x, this x gate, and x gate flips. So as you can see visually, now we can go down. On the block sphere, you flipped. So initially you were like here, and then you flip. So you can play with this. You can create your own functions. Also, IBM Quantum, if you register, provides like a kind of playground when you can put gates like this without coding. Oh yeah, so this is why. We can run this one, yeah. Y will supposed to also give this I imaginary unit. So, or maybe, okay, but I actually didn't present how I work. So like, let's go further. Let's go for the Z one. Or it's Dan. I think it's Dan, right? Okay, that's it. Okay, so now let's go. Thank you, Stephen, a lot. Now now you guys can create your own Jupyter notebooks or use Penny and so on. But now let me finish the talk with I have something in the chat. I'll check really fast. Steve says it's Thursday, so yeah. Okay. Sure. Yeah, now I'm gonna share the presentation again. All right. Okay. So this is the ending of the lecture. So you are solving nonlinear differential equations. So how can we help you? So let's start with not quantum computing or quantum neural networks, how we say, but with classical. So in classical case, you have a neural network, and as an input, you will feed some data. There is a so-called data-driven approach, where you can feed some like vector state, and the output of this neural network will be the approximate solution of differential equation, which is represented here. And the left part, we call it residual, and the neural network basically works by solving and giving you train it, then it will predict you some result and it will give you some approximate solution. So for instance, here, this simplified version of Navier-Stokes equation, the Berger equation, we applied quantum neural network here. No, actually, Yeah, I think it's a quantum network, but now I'm so the idea is here that when you apply a neural network and this is the approximate solution, so you can interpret it. You see the U is velocity, so you see velocities moving in the like with positive and negative components, basically in the velocities. It's like you have parts of the flow with the opposite velocities, right? And when they meet each other, you get in this line, like it's a shock wave. Actually, you can observe it. Like I live in Rio de Janeiro, we have ocean here, and once I observed this shock wave when two waves they go and like they meet each other, and then you get this like it's a shock wave. So this is the solution of this. How you can see. Also, we tested this physics-informed neural network for nonlinear Schrödinger equation. It's how mathematicians call it. Physicists call it Gross-Petoyevsky equation for Bose-Einstein condensate. And here we actually compared even their exact solution of this equation. Actually, it's without external fields, so it's kind of simplified version, but it's nonlinear because you can see this term. And you can see that prediction of this physics-informed neural network is quite good for the coincides actually. And so I actually believe that these results are from quantum neural networks, but if you're interested in this, I will, like, you can just email me later on and we can talk, because our group, we actually applied quantum neural networks to solve to solve these differential equations, nonlinear ones. And now in general relativity, when you have this so familiar nonlinear differential equations, and what could be potentially done. So there is a famous paper, and actually Lucas shared it with me, and the author is Brazilian. Lucas, I don't know, they are all Brazilians, are not, but Roberta Duarte, we talked about her yesterday, João Paulo sounds Brazilian. So this paper is a pioneering work where classical neural networks were applied for the problems which you probably face in numerical general relativity, right? So was the evolution of dynamics of the gas accreting onto a black hole was considered. It's a very interesting paper. I believe you could try to read it and maybe you'll find it interesting. Why am I showing it? Because quantum computing, quantum neural network, it's like extension. It takes part from classical neural networks. So the idea is that if you can apply quantum neural classical neural networks, you can actually enhance them sometimes with quantum neural networks. So if classical neural networks were applied here, I believe that you can create the architecture of like analogous quantum neural network and test on this problem, for instance. So this is the slide we prepared, which I liked, but I don't know if it's really related to the area. The idea is that that your input would be like a four-dimensional space-time, and then you will get the dynamics as output of the curvature of space-time. But I believe it's not only like basically, you know more what set of problems you solve, right? Like the dynamics of the gas and so on. So, but how it would look in a quantum case. So in quantum case, you have a vector state prepared in like in this tensor product. So here you have two qubits, but in fact, better use more qubits because advantage will come with expanding Hilbert space, like 2 to the power of n qubits. And so it could be sometimes that if more qubits in your hands, then you could get some speed up. And so you first do data encoding. You can have classical data, and then you can encode it into a qubit. Like a simple example could be even like 0, 1, 0, 1. You can encode it into qubits by applying those gates. There is also a theorem that any unitary operation, because a gates are unitary, it can be decomposed into a single qubit gates and 2 qubit gates. And this is just an example. So after you apply this block, like a bunch of operators, you will measure the parameters, and those parameters will go to your loss function. So it's like a hybrid, quantum network is a hybrid system because it's like a quantum block, but connected to a classical neural network. And so then the parameters for optimization, to optimize your loss function, they go inside like the parameters, and then you apply some methods, gradient descent, classical methods, by the way, were pretty well developed. And then it's like a loop. And by doing this, you can minimize your loss function, and that would be kind of the algorithm. So we don't know. It's kind of going to be, I guess, your challenge also to think about maybe a collaboration. Maybe we will create something in a group. But we believe that potentially quantum physics informed neural networks can be created for such problems. And here's the algorithm. So on the right side, you see the code written with PennyLane, because PennyLane has more libraries for quantum machine learning. This is the area, it's called quantum machine learning. And this is the kind of simple algorithm. You define encoding, it's a very important part. Then you will define the structure of your quantum circuit, also very important. Then you encode, input, then you measure the expectation value. So you measure those probability amplitudes, the distribution. Then you calculate loss function, take the gradient, apply gradient descent method for the loss function, and they're gonna update the parameters of the circuit. So this is approximately how this quantum machine learning algorithm looks like. So it's a very interesting area to play with. So I guess my talk is like over. So thank you everybody for attention. And yeah, so this talk is supported by the like foundations NPQ and FAPESP. Also the von Braun Center for Advanced Research and Entropic. It's like a company where we offering quantum solutions for industrial problems, to solve industrial problems, not like, so this is the interest of our group. Yeah, so that's it. Okay. Even like,
Okay, sure. I'm
Sure.
curious.
do I have any questions or messages? You can try to ask me some questions or share with me if any, at least.
So yes, I have a question. I just typed
Is
it
there
in.
much understanding yet of how to formulate these quantum network problems? Okay, what do I mean much understanding yet? In terms of like there are several problems actually in all of this. I would honestly, I want to say something that this is pretty cool what we're doing. We actually, if anybody, one of us decides to actually try to apply quantum computing to numerical general relativity, it's immediately going to be the pioneering work, because I believe nobody yet did it. So by doing this workshop and this talk, we're already sort of creating emerging field, new field. So much understanding about quantum neural networks, well, that's enough. Any guidance, many algorithms I have seen to be unique and bespoke. Look into quantum machine learning. So quantum neural networks, study PennyLane library because they are really kind of full of this. Be in touch with the community. You can contact with me or just like, I showed email. So my email is Victoria Porozova. I also do some kind of educational quantum computing, quantum mechanical and theoretical physics on my Instagram. It's exactly the same, Victoria Porzo. So you can contact me the way, yeah, you can find. And because I think in our group, we maybe will try to even also find some quantum neural network for the task. But for us, it would be problematic because we're not specialists in numerical general relativity. So the idea is to define the problem. So you have to first define the problem, and then you have to map it to quantum like solution. and probably it's going to be hybrid. It's going to be AI like methods deployed and so on, and there are some quantum inside. But I think it's very interesting. Whoever writes the first paper is gonna make some noise. Like it's gonna be pioneering. Also, there are quantum schools. So the class enhanced screen doesn't mean they reduce time complexity. I think so. I think so. There are some like always like logarithmic approximations. So the idea is that it should actually enhance exponentially because the power, like the Hilbert space, grows exponentially in quantum case, right? Because it's if it's qubit, by the way, it can be qubit, could be even d-dimensional, but for qubit, so it's 2 to the power, okay, 2 to the power n. If n is small, like 2 qubits, 2, 4, and so on, then classical and quantum, they will go like this. But when you grow the amount of qubits, it will go like exponential. You will get the gap between classical and quantum. So far, people didn't get the exponential speed up though. They get only like a polynomial, but it's also good. Even if you do some speed up by factor 2, for some industrial problems, it could be like a big deal. You save a lot of money. For fundamental research, well, I guess so, like in terms of power. I think it's should be tested, right? So like if you will have to find some physics informed neural network for the problem, for a specific problem you're interested in, then you run. Then you try to create quantum version of your physics informed, and then you do benchmarking. And then you can see if there is a benefit, like it should be tested. But before I met this group, and we talked with Lucas, and I was more skeptical about quantum neural networks. But in this group where I work now, they're getting like speed up with quantum computing algorithms. Yeah. So there is a potential we should explore. So if we could use kernel, we could use quantum informed, or I think it's called like quantum physics informed, if I'm not mistaken. I don't know, probably like this. But it's already quantum computing, because quantum computing, it's like quantum computing, quantum simulation, quantum machine learning inside. So it's like it's a set, and quantum machine learning or quantum neural networks is a subset inside of it. So yeah. I believe better to start with from this side, from like quantum neural networks. So if we could use spin, then yes, that's my idea. And I asked the colleagues, the experts, they said the same. They have similar idea as I do. It makes sense, right? Because it's like the proposals that are can be, it's one of the advantages that quantum computing or quantum networks can sometimes like speed up some already working, but should be done. The work should be done here to check. We don't trust anybody. But in my group where like I worked, they applied quantum computing for like warehouse problem, and now they are for like we're doing patent on this because we got some speed up for logistics problem, basically for allocation of details of car. So if we can do it with this, I believe we can do. It's just sometimes we don't know how. So okay. Somehow I got on time. So I hope you enjoyed. I guess it was unusual talk for the audience. Thanks. Thank you for the invitation. Should I stay and listen? I think I'll stay, maybe listen to the next talk at least. So thank you so much.
Thank you.
Yeah, so it's time for a break. Okay.
Yeah, well, can't hear you well.
Never worked.
It's still obviously, but